Okay. Okay. So, good day, everybody. Welcome to the seminar series on critical transitions in complex systems. Let me first introduce the seminar series and its objectives for some of the new people who have joined. This is a seminar series being jointly hosted by IIT Madras in India and Potsdam Institute for Climate Impact Research, Germany. The seminar series brings together experts from diverse fields such as climate science, neuroscience, ecology, fluid mechanics, etc., and aims to disseminate the state of the art in the prediction of critical transitions in these diverse fields of study. The seminar takes place every month on the last Monday of the month, so mark your calendars. Before I introduce the speakers, a few housekeeping notes. I request everyone to turn off their microphones and please use the Q&A box in Zoom to ask the speaker your questions. There will be time in the end to answer the questions. With that, let me introduce the speaker today. Actually, she needs no introduction, but for the sake of formality, I will introduce Sarika. She is a professor at IIT Indian Institute of Technology, Indore. She earned a PhD from Physical Research Laboratory in Physics, followed by a postdoctoral fellowship at Max Planck Institute in Maths in Leipzig and Max Planck Institute for Physics of Complex System in Dresden, Germany. Professor Jalan has been part of various national and international forums, namely, she is an elected executive member of Complex System Society, member of Complex Science Institute at NTU Singapore, National Advisory Committee for CNSD. She was awarded the prestigious SCRB Power Fellowship by the Department of Science and Technology. She has held various visiting scientist positions at some of the prestigious institutes across the world. I will stop with this because there are too many honors to be read. And I'll take up all the time. So I think I'll stop with this. So Sarika works in the broad area of complex systems, nonlinear dynamics, and her current research interests are synchronization, higher order interactions, coupled oscillators, and applications to financial and power grid systems. So the floor is all yours, Sarika. Yeah.
Mute. Okay, now I should share my slides.
Yeah.
Okay.
But
and I have to
can you get into full screen?
Play from start. Okay.
Yeah, wonderful. Yeah.
All can see my screen, and I'm so thankful for Sujit and Jürgen for such a wonderful, for providing me such a wonderful platform to present my latest work. So you see, like you all know about, or some of you might have heard about all this coupled dynamics or coupled oscillators on networks. And last few years, like namely from 2020 or 2019, has seen a spurt in activities in higher order interaction. So my talk, so last 3-4 years, I have been also be very much interested in coupled, to understand that how this higher order interaction, I will introduce all these words as we'll proceed. So Sujit, how much time I have? I forgot to ask this thing. How much time is
you can speak for 45 minutes approximately,
40 minutes.
Then 40 or 45 minutes and 10-15 minutes for questions.
Sure. So I will keep on introducing all these terminologies as I will proceed. So I have been interested in the coupled dynamics on higher order interactions. And before I proceed and I forget, let me tell that this work I have been doing with mainly with these two very young and talented PhD scientists in my lab, PhD scholar in my lab, Priyanka and Ayushi. And recently Abhishek has also joined and has been contributing here. So okay. So this is like I will be using coupled Kuramoto oscillator in order to demonstrate that how higher order interactions can bring out something which is not possible for the same system if we consider only pairwise interaction. And I am going to use, so there are various systems which people have been using, but I will take this, my favorite, this coupled Kuramoto oscillator, this phase oscillator, to demonstrate some of the properties which higher order interactions that brings up in a system. So this is like beyond pairwise interaction. And today I'll take example of one of my latest work, because last 4 or 5 years have witnessed the spurs in the activities. And I will take one example where I show the finite size effect. And let me proceed as I am building up all these terminologies. I will keep on demonstrating. And this is higher order interaction, which I have tried to capture here. So, network, which we all must be knowing now by this time, that network have been very popular to understand the properties of complex system. And but network captures only pairwise interactions, whereas functions of many real-world system. And one of the very good example which we have been seeing since our schools, that we have chemical reactions. So A plus B leads to C plus D, and you cannot have pairwise interaction when we want to capture that chemical reactions. So in the similar fashion, there are several enormous things or functional things which is not the part of the pairwise interaction. So if you want to capture, suppose, a chemical kind of chemical reactions, if A plus B is leading to C plus D, we cannot say that A and B are pairwise interacting or A and C is pairwise interacting, because it's a combined 4 nodes interactions altogether. And if we remove 2 nodes, then we cannot actually define that interaction. Similarly, for a scientist, we can have this higher order scientific collaboration network. So if 3 scientists have written a paper together, and if you want to write down the network architecture, and if your A, B, C have published a paper together, it's completely wrong if we write down the A's between A and B, or B and C and A and D, unless and until they have separately also written the paper together. So such kind of things have been, we had been knowing this thing for a long, but it has been started emphasized actually relatively recently. From last 4 or 5 years, have seen a lot of activities. So ecological systems, 3 or more species may compete for the food or territories. Online or offline social networks, or WhatsApp groups which are there, where all the people, they are communicating simultaneously, or any consensus is reached because of the group interactions. Gene regulatory network, spreading of consciousness or contagious disease. And then there are several actually data science with the data in the real world data. They have tried to show that many real world systems or data have interactions which is beyond pairwise. And there are a few early work which I have quoted here, and there are several works now since last 4 or 5 years which have been seen. And recently we have, I would like to advertise this physics report, where we have written with other authors as well on, and whatever I am going to talk about, that is already listed in this physics report, couple Kuramoto oscillator portion. If you see, so all the things which I am going to talk today is one can easily find out in this review article, particularly in that chapter. So with that, let me also define, like when we have pairwise interaction, we call it mathematically one simplex, because there are 2 nodes, it's a one simplex. And as soon as we have triangle interactions, we call it 2 simplex, and so on, like 3 simplex and so on. And let me now quickly go to the model, which is very popular model, because first of all, it's very simple. You can see that this model. So let me first explain this model, and then I will tell that why this model is so popular. So here you can see that suppose you have n interacting populations, and you want to understand particularly the synchronization phenomena. So this model has been very popular to understand the coherent behavior arising due to interaction in n population, n interacting, nonlinear interacting units. And you can see it's a very simple model, because it has only one variable, which is the phase, which is known as phase, because it is rotating between 0 to 2 pi. So one can safely call it phase. So phase of ith oscillator with time, that is evolving with its intrinsic frequency. So if there is no interaction, you can see, depending upon the initial condition and frequency, you can say whether there would be synchronization would be there or not. So if initial conditions are different, or frequencies are different, you can never achieve the synchronization. Synchronization means same behavior for t greater than t0 for all time t greater than t0. So you can see that it is completely dictated, the phase is completely dictated by the intrinsic frequency or the initial conditions. But as soon as you introduce this interactions, so you can see this is the coupling strength K, n is simply normalization factor. You can right now, you can just simply ignore that. And this is the nonlinear interactions which so ith oscillator is interacting with all the jth oscillators, very simple model. So each oscillator is interacting with all other oscillator with this nonlinear coupling function. So this is very simple model, one dimensional. This is the nonlinear function, and because of this nonlinearity, it ensures that depending upon k, you can get super rich behavior. And this model has become so popular, like including synchronization. Then you had chimera state, which was shown using the same oscillator, of course, with the some phase phase lag was also there, and you had identical oscillator. But this oscillator has keep on giving very nice phenomena. So weak coupling also, it has been demonstrated to show chaos. So I am not going into that direction chaos. I am just focusing on the synchronization, which is still like one of the very fascinating phenomena still, despite of so many decades which has been gone. So synchronization here is phase of ith oscillator that is equal to jth oscillator for all time t greater than some critical some initial transient time. So this is the oscillator, and then this oscillator has seen a lot of applications, like applications to power grid. This is the few examples as I am here just mentioning. So I am not working on the power grid, etc., but there are some examples on the power grid. So where the nodes are the power generator and the links are the transmission lines. And a bit of variation of this phase oscillator, where you have nonlinear coupling term. Now, instead of all-to-all, you have this network structure, because we are talking about the real-world system. And as soon as we have real-world system, you can see it's a finite. All real-world systems are finite. Today, I am going into that direction. That's why I am already building the stage that all real-world system is finite. And some variation of this phase oscillator. Now you have inertia term and you have frequency term, but some variation has been used to investigate the power grid, and a lot of work has been done. It has been emphasized that this Kuramoto oscillators, the variation of this generalized Kuramoto oscillator provides a very simple model to study the behavior or the failure of the synchronization failure in the power grid. So this is one of the paper from where I have just taken this stuff. And then brain network. Brain is so complicated again, but still the firing of the individual neurons was again modeled using this Kuramoto oscillator in this fashion. So dynamics on the brain network. Again, you have this non-linear sinusoidal kind of interactions, intrinsic frequency. And then you have WIJs, some brain connectivity matrix, synchronization between various nodes in the connectome. So this have been investigated. So here's just few examples to show that this model has seen its applications, apart from the fundamental thing, which was also very fascinating. And Strogatz also did very beautiful article, which was in 2000. And I suggest actually all the youngest PhD students to read that. Fiska D 2000, Strogatz has written very beautiful review article, Kuramoto to Crawford, and several fundamental questions about the coupled Kuramoto system he has proposed. So apart from application, this coupled Kuramoto oscillator is very good for its fundamental point of view as well. Okay, so let me now show you why it's so interesting and what I want to today. So this is, I am building up the background. So first I will show, so the plan, so my plan is, first I will show in the pairwise interaction, what coupled Kuramoto oscillators show. Then I will introduce the higher order interaction, and I will show that what is the higher order interaction, the background. And then I will show that what is our work, which is the finite size thing. So let me now tell you, so this is the coupled Kuramoto oscillator. So entire, actually my talk, mainly my talk will revolve around only this simple mathematical equation. Okay, so it's the same mathematical equation you can see, and now I am defining this complex order parameter, which is used to measure synchronization. So you can see this is a complex order parameter Z. R is the real part, and e to power I psi, and that is given by this summation over e to power I theta j, and this is just simple the averaging. So it's an n number of oscillators, so it is 1 upon n. And you can quickly see that if I take the mod both sides, we get a real number R. So that is the measure of the synchronization. Okay, so when we take mod both sides, then R becomes the measure of the synchronization. And then you can see that if all oscillators are same, so all thetas are same, so this can come out, and then R is equal to 1, that shows that all oscillators are synchronized, and R is equal to 0 shows that all oscillators are distributed uniformly in that 0 to 2 pi circle. Okay. So this R provides the measure of the synchronization, and this model can be solved very well to obtain this t tending to infinity, that limit of the order parameter as a function of k. And this I am skipping. I am not showing this mathematics here, but you can see in that paper by Strogatz, which was I was showing. This is one of the very nicely written paper. So now here I am just showing you the infinite time limit behavior of R. So in the beginning, you can see this is something very interesting. So let me now close this one. Okay. So you can see that as k is increasing, so the k is the coupling strength, and why this Kuramoto oscillator became so popular, because you can see that in the beginning, R is equal to 0 remains the only stable solution. And as at critical point Kc, there's some bifurcation. So there's a phase transition. So this is a supercritical, this is supercritical pitchfork bifurcation, which, so I am not showing here. There is another branch here, which is for R negative, but R negative does not make any physical meaning. So we are just plotting here our positive thing. So it is supercritical pitchfork bifurcation through which this R is equal to 0 state loses its stability. So this becomes unstable, and you have a smooth transition to the synchronization. So because of such kind of critical transition, this model, this very simple model that immediately actually gained a lot of attention and popularity. So that happens with the pairwise interaction. So pairwise interactions, what happens that as you are increasing R at critical coupling strength Kc, some oscillators comes closer, and then as you keep on increasing K, that more and more oscillator, which is deviating from, you can see this omega is the intrinsic frequency distribution. So first those oscillator which are very close to the mean frequency, they start getting synchronized. And as K is increasing, then more and more oscillator keep on joining this synchronized cluster, and very smooth transition to synchronization occurs. So this is known, and I would like to draw your attention to this fluctuation, because this is something important for my contribution, our lab's contribution in this, like today's talk, the prime result of which I want to emphasize. So you can see there is some fluctuation in K, correct? So, so here what I have plotted here, I have plotted T versus R. So this is again taken from the same paper by Strogatz in 2000, where he has taken the same model, and now you can divide your phase space into two parameter. One is like above Kc and one is below Kc. So below Kc, you can see that all oscillators like R is equal to 0. It means oscillators are moving in the randomly moving into 0 to 2 pi by taking 0 to 2 pi phase. So now this below diagram, you can see that is K less than Kc. And as we are increasing T, so in the beginning, so you can see asymptotically R is becoming 0, and there is a small fluctuation here. And that would be the order of 1 upon root n actually. So this fluctuation that depends upon the number of oscillator, and this is the important point. And same thing like as K is greater than Kc, you have also some fluctuation. Okay. So this depends upon the number of oscillator, because you do the simulations and everything, which is with the finite number of oscillator. So all the analytical plots, that is for the continuum limit in finite size, but reality when you do simulations, it is some finite number of oscillators which are there. Okay. So now we have this oscillator, and weak coupling chaos, strong coupling, you get synchronization. This is the order parameter. Order parameter takes value between 0 to 1. 1 means you have synchronization, 0 means incoherent state. And this is the thing which we know. And so you can see that this is the logged oscillator. So as you keep on increasing K, what happens? Some oscillators, they come closer together, become logged, and some oscillators are still drifting actually. So at this point, you have coupling strength strong enough that some oscillators like this criteria is getting fulfilled. And you can see as K is increasing, so it is like feedback phenomena. K is increasing, R is increasing, and this condition will get satisfied for more value of omega I, which is away from the mean value of omega. So with that, you will have more oscillator which gets logged, and Strogatz has proved also that drifting oscillator have the zero contribution in the synchronization. So drifting oscillator don't make any contribution in the R. So only the logged oscillator, they make contribution into R because of you have symmetric frequency. So as soon as you have symmetric frequency, you have the same number of oscillator at theta I and same number of oscillator as minus theta I, or same like omega I and minus omega I, and they cancel together, cancel each other. So that's why drifting oscillator, they don't make any contribution into R. So one has only the logged oscillator, but this is only applicable for this model. As soon as we have phase lag, etc., my statement is not true. So whatever statement I am making here, that is only for this particular model. Okay. So if you take some variation like phase lag, etc., then drifting oscillator also makes contribution, but not now. Okay. And right now in my talk, I'm not taking the phase lag. So it's all like logged oscillator will make the contribution. So now what I have done, so this is already the work which has been done, and so much understanding which we have if we change omega, if we have phase lag, if we have network structure. So many things have been done, and I will come to the analytical approach, and let me introduce first this thing which is I am going to talk about. So now we have phase oscillator, but instead of pairwise, we are taking actually instead of phase oscillator, we are taking, just 1 second. I'm sorry. I have this new phone. I don't know how to make it off. I'm sorry. Okay. So now we have phase oscillator, and we put into the higher order interaction, and let's see that what happens. So coupled Kuramoto oscillators on hypergraph, I'm using the word hypergraph, but what I'm going to show you, that is the simplicial complex. Simplicial complex means link the clique of order n. So it's like more like this. Okay, so right now it's a hypergraph because I have not taken the pairwise interaction. So here now you can see I have the same Kuramoto oscillators, but instead of pairwise interaction, I have taken this triangle interaction. Okay. So now you have omega I, which remains same as for the pairwise interaction, and K is the coupling strength, and I have this normalization is n square because now summation is running over J and K both. Okay. And now you can see this is a nonlinear interaction. So this cannot be decomposed into the pairwise interaction in any manner. So this is because of this nonlinearity, you have this triangle interaction which cannot be decomposed into the pairwise. So you can see theta j plus theta k minus 2 theta I, the simplified version, but you can have any combination of triangle interaction here as long as it's a nonlinear, which is the sinusoidal term. And now summation is running over from j k to 1 to n, and that's why I have normalized here with n square. And you have the coupling strengths. We don't have any pairwise interaction. And if I'll be giving this talk offline, I would have asked that what you expect. But since it's online one, I'm not asking this question. But now you can see as we are increasing this K, here I have written K2. K2 indicates a simplicial complex of order 2. So which is this one. So here K and K2 is same actually. So as we keep on increasing this coupling strength, you can see that R is equal to 0, solution remains the stable solution for all value of K actually. So which was not the case when we had the pairwise interaction, because you can see there was a phase transition, the supercritical pitchfork bifurcation through which R is equal to 0 state was becoming unstable. But here R is equal to 0 state remains stable for all value of K actually. So you take whatever value of K, analytically one can show, one can take, so I will show that also, that you can actually have the reduced order parameter and you can do Jacobian analysis and you can show that R is equal to 0 state remains stable for all value of K. So you don't get any synchronization here, okay? But in the forward direction, but what happens if you start with the synchronized state? It means if you take theta j is equal to theta I for all ij, then what happens that if you start with the synchronized state, just follow with me with this blue line, forget about all other this one, because I want to proceed with the new thing which I would like to talk about. So suppose we start with all theta same and I decrease K, then one can see that this goes to the jump to the this R is equal to 0 case with the saddle node bifurcation, and there is a one unstable orbit which is here. So forward direction, because this two stable state that is actually separated by one unstable orbit, which is not shown here in this figure. So depending upon which attractor basin of attraction we are having, which collapse to either this one or this one. So if we start with all oscillators homogeneously distributed, R is equal to 0 basin, then we always remain here. But if you start with R is equal to 1, then we are here. And after that, you have this saddle node bifurcation, and you have only one global attractor actually. So in this region, you have two attractors. So this was the explosive desynchronization word, which was there, and we did some work. So it started with Skardal-Lerna's atlas, as far as I know, in 2019. And then we have, actually, there was one work by Pazov with the homogeneous frequency distribution, and there also he showed this explosive one. But okay, so, but their frequency distribution was actually smooth and homogeneous, and here the frequency distribution could be anything. So this is the thing. So now if we have explosive desynchronization, and let me now come to the analytical part here, and I show that analytics, whatever analytics predicts, that is for in the continuum limit. It means when n is very large. So whatever analytics we do, that is in the thermodynamic limit by assuming that n is very large. Okay, so first I showed the analytical part to show you that, because, and then I will show that when I have finite n, how we get a different behavior which was predicted with the analytics, and entire things lies in this analytics. So this is very important here. So now we have, you see this pairwise interaction. So let me start with a very generalized model. So I have this pairwise interaction, sine theta j minus theta I, which I had introduced in the beginning, and now I have this triangle interaction as well. So I have pairwise and triangle. For pairwise, I am saying K1 because it's a simplicial of order 1. And for triangle, I say K2, the overall coupling strength, simplicial of order 2. Normalization here is n because you have n summation, and here normalization is n square. I have the same frequency distribution, which I had been taking from the beginning. And then now you can see, because of this all-to-all coupling, I don't have any network structure still. One can, actually, the thing is that now in order to do analytics here, you can see this is n coupled differential equation. So for analytics, what actually this Ott and Anderson proposed one very nice answers, and that was published in Chaos Journal in 2008. And that is one of the most popular and beautiful paper, in my opinion, so far in coupled Kuramoto oscillators. What he did, this n-coupled oscillator, he showed that how one can reduce the dimension to only 2 dimensions. So here you have n-coupled oscillator with n, this is increasing. And he told that you can directly get the differential equation for R. Okay, and you can solve using Jacobian analysis, etc. And very beautifully you can do entire analytics. So for that, actually, first one has to write down this equation in terms of mean field. So you can see this entire summation you can get rid of, because that is already coming in R. Because if you can remember, R was nothing but e to power summation over e to power I theta j. And if you equate, so you do some small mathematics, you can actually get rid of, you can substitute this R1 instead of this summation over. So you see that we have got rid of this summation over term here. And actually, the physical thing about this equation is that now, instead of seeing all the oscillators here, so here this oscillator is seeing all other oscillators, but here you can see each oscillator is seeing one mean field, okay? So each oscillator is affected by the mean field, because R1 is nothing but the summation over e to power I theta j. And this also, similarly, this also very simple mathematics. I can also explain it later on also, and you can mail me also. And this is there in all the papers. You can see that very simple algebra one can get from here to here, where R1 is the global order parameter, and R2, I'm sorry, I did not introduce it before, but R2 is the order parameter, cluster order parameter. So instead of e to power I theta j, it would be e to power 2 I theta j. Everything remains same here. So in steady state means theta I dot is equal to 0. There is one sign which is missing, theta I dot. So in the steady state, theta I dot is equal to 0. So one can write down and psi 1 and psi 1 psi 2. One can assume that they are 0 for the symmetric frequency distribution. Actually, one can prove that psi 1 also becomes 0, which is the mean phase for global order parameter, and psi 2 is the mean phase associated with R2. that for the symmetric frequency distribution, one can see that one can actually prove that that becomes 0. So in the steady state, this sine theta 1, that is equal to omega I upon q, where q is given by this. Okay. And now you can see that this sine theta has to be, mod of sine theta has to be less than 1. So from here, very well, we get that mod of qi has to be less than q. So you can see this minus q to plus q. So any oscillator which is coming within this regime, that will get logged oscillator. And other drifting oscillator for which their omegas are greater than either less than minus q or greater than plus q. And the stationary state, this R will have some fluctuation that please recall that 1 upon root n. So these are the only thing that R will have some fluctuation. Okay. And then by doing this odd intention approach, which is not the actually motive of my present talk, and this is there in almost all the papers which appeared actually for any non-identical oscillator paper after 2008, you can see any paper which talks about the coupled Kuramoto oscillators, non-identical, they have actually derived this entire system using the odd intention approach. So this you can find in all the papers, including the papers which you can see from our published paper. So one can see that from n differential equation using the odd intention approach, which I am not detailing here, one can get actually a differential equation in terms of r dot and psi dot. Okay. And psi dot is equal to omega 0. So if you take mean frequency 0, then psi dot is equal to 0. And here now you can see that this r dot is nothing but minus r delta, where delta is, so one thing which I would like to remark here, this odd intention approach mathematically is only possible if we take this frequency distribution, Lorentzian distribution, because there is one step which comes there in odd intention approach when you solve this R in the continuum limit, that you get this contour integration, and that is only possible to solve when we have this Lorentzian distribution or any kind of bimodal distribution. So because of some integration, complicated integration, this odd intention approach, one can actually apply for such kind of Lorentzian distribution. So here delta is nothing but this parameter in the Lorentzian distribution. So minus r delta, so plus k1 upon 2 r minus r cube plus k2 upon 2 r cube minus r to the power 5. So you can see when you have this, so if k2 is equal to 0, you can see this equation has 3 solutions. Okay. But as soon as we are having higher order interactions, so you can see the solutions becomes more. This is something very mathematical. So as you keep on increasing more and more higher order interactions, the dynamics becomes more rich or complex, because you have more possible solutions. Correct. Whether they are stable or unstable, one can do very simple Jacobian analysis. So but first thing is that r dot is equal to 0. One can solve this equation very well, because this is the simple one order equation, and one can find all the roots, and then one can do the stability analysis, and one can see that which root is stable or not, and one knows the entire phase diagram. Okay. So this is the beauty with this odd intention approach, that now we can have entire phase diagram without doing any numerics. Okay. So this, let me skip this one. I can come back again. So let me now show this entire dynamics actually. So this is for some K2 value of 10. So you can see that it has 5 solutions, 1, 2, 3, 4, 5. Okay. This solution is the negative regime. That's why in papers you will not find this one, because R negative does not make any physical meaning. Only R positive has the physical meaning. And now let me explain here. This is some mathematics, very simple mathematics. So for those who have done courses in nonlinear dynamics or in the Strogat's book, one can do this. One can get very simple stability analysis. But now you can see that for as k is equal to 0. So this is for as k1 is changing and k2 one has made fixed, suppose. So as k1 is increasing, one can see that this R1, so y-axis is R1. R1 is equal to 0 actually remains a stable state, and one can actually do this stability analysis. So it loses its stability exactly at 2. So one can find out the other solution, one can give a small perturbation, and one can see whether that Jacobian has, if it is negative, then it means that its state is stable. If it is positive, then its state is unstable. So one can see that as one was increasing K1, exactly at K1 is equal to 2, that dark line. So dark line resembles here the stable solution, And this light lines, they represent unstable solution. So here exactly at this point, actually, you have this R is equal to 0 solution loses its stability. It becomes unstable, okay? And this unstable solution, actually, they evaporate, they don't exist here, these unstable solutions, because those roots become complex, so one can have only real roots. So this solution evaporates, and another stable solution that arises, which is this. And this is known as nothing but the pitchfork, subcritical pitchfork bifurcation. And so now you can see here in this design, if you pay attention to this region, one can see that there is a there's two stable branches, and which is separated by one unstable branch. Okay. So now the finite size effect, which I am going to tell actually. So the thing is that now we all know, like this is very established in hypergraph community, that because of hypergraph, one gets the this subcritical bifurcation, or which is known as explosive synchronization, first order transition to the synchronization. So you get the first order transition to synchronization. And when you're reversing back adiabatically, because now you are in this region, so since you are in this basin of attraction, you keep on reducing the K and you remain synchronized. And here, when you have only one global solution, the solution jumps back and you get one stable solution. So this is the thing which we all know, which is predicted analytically in the thermodynamic limit. But now, before I show the next slide, which is actually results for the finite dimension. So now you see that this all results for the continuum limit, and which predicts that at K1 is equal to 2, we get the synchronization, okay? But you see that as we keep on decreasing n, if you recall that the fluctuation in R is the order of 1 upon root n. So if we have fluctuation becomes larger, and the fluctuation is suppose higher enough to cross this unstable branch, then what will happen? The trajectory will jump here, despite analytically we have not predicted that trajectory will jump here. Suppose at K1 is equal to 1, suppose if my n is smaller, it means my fluctuation in R is larger, and then that fluctuation is large enough to actually this shoot this barrier. So as soon as the fluctuation comes here, this is the stable attractor, so my trajectory will get attracted here. So because of this unstable region, you can get, and I think this Pikovetsky has already shown such kind of things, not for the higher order interaction, but he has already demonstrated that whenever we have one unstable regime in between, you can get the synchronization because of finite size effect, and which is actually not predicted when you have continuum limit. So now this is the entire diagram for higher order interactions. So first order transition to synchronization at K1 is equal to 2. So when you have all-to-all coupling, this is the all known. So as you are, so you can see here, so this is the known result. So as you can see that when higher order interaction is not there, you have supercritical bifurcation. And as soon as you have higher order interaction, it means K2 plus 3 is not 0, you get a jump. And this hysteresis width is actually governed by K2. But now you see that, so if K2 is equal to 10, then I can get the synchronization even here also. Even below 0 also, we can get the jump to the synchronization, because you have unstable, you have two stable regime. So if my fluctuation is large enough, I can actually get the synchronization, even the negative regime as well. So as we keep on getting K2 larger, my jump, actually, the transition to synchronization may get earlier because of the finite size effect. So depending upon K2, for same size of the system, you may get synchronization transition, even though that is not possible in the thermodynamic limit. And let me show this result actually. So this is the result actually. So now you can see that when we have only supercritical transition, only pairwise interaction, when K2 is equal to 0, since always we have only one stable branch, so there is no jumping, and we don't get any finite size effect, because in order to witness the finite size effect in this particular system, you require two stable branch separated by one unstable. But here always you have only one stable branch. correct? Here r is equal to 0 was stable, and here 1 minus root over, like root over 1 minus k upon k2c was one stable branch. So you, depending upon, so despite the, you can see that bottom, your n is larger, and as you keep on decreasing n, you have more fluctuation, but you don't have any jumping because you have only one global attractor. But as soon as we have K2, so K2 always have one unstable branch, which is depicted here. So this is your analytical prediction, which happens as K2, and this is the unstable line. So one can see that n is equal to 50, which is the very small size. The fluctuation in R, which is larger, you can see 1 upon root n kind of fluctuation. And it may be possible that because of this fluctuation, you can have jumping. So same like for, as you can see that for larger network size, fluctuation is smaller. So you will have, you cannot surpass this unstable branch. So as n is increasing, since fluctuation is becoming smaller, you require a smaller value of this unstable branch in order to get jump. But for very small network size, even you can get jump at 0 itself, where this prediction is at 2. So this is for K2 is equal to 8. For K2 is equal to 10, you know that this hysteresis was coming into the negative regime as well. So it may be possible that you start getting synchronization in forward direction in the negative regime itself, just because of the finite size effect. Okay. Then we did a lot of analysis here, like exit probability, etc. But I am not actually going to tell about the several stuff, but let me demonstrate numerically what is happening here. So here, so this first graph is in the incoherent state. It means that you have this, so when there is no jump, you can see that when there is only one stable branch. So suppose we are here, so this is unstable branch is here, but if I am taking my coupling strength here, so even though my fluctuations are larger, there is no place to jump because only one stable attractor, which is r is equal to 0. But as soon as we are, suppose in this regime where you have two stable attractor, as soon as my fluctuation is, suppose this is the unstable branch for one particular value of K1, and this I am plotting in time. So I am starting my simulation, okay, for one particular value of K1. And since there is some fluctuation in R because of the finite size, as soon as this fluctuation actually crosses this unstable branch, you get a jump. So you see now here it has not crossed, but at one particular time t, it may be possible that fluctuation actually that crosses the unstable branch and we get this jump. And we have done like all the probability distribution and a lot of numerical things here, not still analytical stuff. So we have provided the understanding, but we have not provided the analytical calculation for the finite size, but a lot of numerical like exit probability, first exit probability kind of very interesting investigation, which we have tried to do. Okay, so you can see it's a time dependent because if we have a smaller time, we never see the jump. But for larger time, for any value of K1, actually, we will see the jump. So even though in this unstable regime, if we take T very large, there will exist one T when fluctuation is very large and we will get the jump. So it depends upon T. If we run our simulation for a smaller time, then we may not get jump. So since all the real world systems are finite in size, so the analytical calculations which are done in the continuum limit, for that we may not find that there would be synchronized solution, especially one thing which I would like to draw your attention, which is in this plot, where I have shown that in the forward direction, there is no synchronization. But since I have already told you there is a one unstable branch, which is coming from here and going to the infinity. So there's two stable branches. So even the forward direction in only pure triangle interaction, we can see the jump. That is the point. So with that, I think we have several understanding here, but numerical, all of them so far numerical. So fluctuation in finite ensembles of Kuramoto oscillators can induce phase transition when no critical point exists in the thermodynamic limit. So with effective critical points, so there's no critical point exists in finite size. So that is the one take home message which I would like to mention. So with effective critical points determined numerically, and transition mechanism in system with higher order interactions. So because of bifurcation, you have bistability here, allowing the this order parameter to, so there's a probabilistic transition between incoherent to coherent. So not deterministic. You don't know when that transition will occur, but at some particular t, when you have this fluctuation crossing that unstable orbit, you will have transition. So dimension reduction and a fixed point, the Otto-Intenson methods that gives a relation for fixed point in thermodynamic limit, but the finite size systems, they form a stationary state that fluctuating around those fixed points. And the future direction, of course, that using real world networks, because it's all I have still shown for all to all. As soon as we have real world kind of thing, when analytically it becomes difficult, and then whether something is arising because of the finite size or because of the network architecture, that is also difficult. But okay, this is the entire future direction, open area, then multi-layer structure, and etc. So with that, I would like to acknowledge this SERB Power Grant Vajra project, and a few of our recent publication, including this one, is available in the Google Scholar. And with this, thank you very much. I think I was within time, correct?
Yeah, yes, absolutely. Thank you for this very nice talk. So I request the audience to type the questions on the Q&A box. Already there are some questions. Sarika, you can see them?
Yeah, I can see them.
Yeah.
Expecting question from you, no host and panelist,
Uh,
every. I have to
No,
put
the
it.
Q&A box, not chat.
Uh,
First
no,
question is from Chandrakala Meena.
so where I have to more, this is more Q&A. Okay.
Q&A, yeah.
If we change dynamics from deterministic to stochastic, then also, so stochastic, no, as soon as you have stochastic dynamics, the Otto-Intenson approach, we write down continuity equation. But as soon as you have a stochastic equation, we have to write down the Fokker-Planck equation. Okay. So with the Fokker-Planck equation, actually recently, of course, I can give, there's a lot of work which has been done with the pairwise interaction. I don't remember the name, but recently we have done for higher order interaction one work where we have taken the Fokker-Planck equation, but analytically it's not possible to solve the entire, so we cannot get the equation in R dot analytically, but it's a semi-analytic way, I would say. So I will send you, Chandrakala Meena. I will find out this particular reference, and I will send to you. But Otto-Intenson is for continuity. When we have this continuity equation should be applied. As soon as we have a stochasticity, noise and stochasticity, we have to have Fokker-Planck equation. So, and I will send you the reference. Yes, please. Second question by Rohan. So did it answer your question, Chandrakala? Okay. So Rohan has a question that from higher order interaction, we saw that the nature of transition changes from supercritical to subcritical. Is it also possible to get a secondary bifurcation with higher order? What do you mean by secondary bifurcation? Because you think that if we go from triangle interaction to quadratic, so until quadratic interaction, you get only R to power 5. So you have only 5 possible solution. Now one can actually very straightforward, one can do with Otto-Intenson approach, and one can see if we take quadratic like this simplicial complex of order 4, then whether you have more bifurcation. But I know one thing, that if you have multi-layer, then you have dynamics becomes richer. But if you go from 2 simplicial, 3 simplicial to 4 simplicial, I don't know, but one can actually solve this thing very well, because Otto-Intenson approach is very lengthy, but very straightforward actually. So one can solve and can see that R dot equation has how many terms. Right now it's R to power 5. So we have 5 solution. If we have R to power 7, then we have 7 possible solutions, but I don't remember doing that or recalling discussing that. So I cannot answer you whether we have more possible solutions or not. Okay. So if we have Ira Rai has the question that if we have 4 Kuramoto oscillator, okay, with nearest neighbor interactions, okay, 4 Kuramoto oscillator in a ring, and different initial conditions arranged in a ring topology, will we see any symmetry in the dynamics of each oscillator? So I would say it depends upon the frequency. If it's identical oscillator, then one can actually talk about the symmetricity. But as soon as you have unidentical oscillator, like if you have some frequency distribution, then this symmetricity gets lost because it's all determined by the frequency, not determined by the initial phase. So with the four oscillator, I know that this kind of, what is the splay state kind of things, which Reza D'Souza has done a lot of work on the splay state. And there I've seen they work only with the 4-5 oscillator in the ring. And they talk about many different kind of, such kind of states, like in the ring, they take different initial conditions and they named it splay state, a splay state, which I didn't understand that time, perhaps nicely, so I cannot recall them. But as I understand that until you have identical oscillator, this frequency dominates more than the initial conditions. So Sneha has a question. This is a very informative. I thank you. I really like the last point about probabilistic transitions. Would you happen to know if there is application of this concept to, actually all real world systems are a finite size. So like one like something which I experienced in my lab last year. I had one student from ISR Mohali, Akanksha. She came for master project in my lab, and I gave her some simulation, and she told me that she is getting transition when we have triadic interaction. She told me that I am getting transition into the forward direction, and I told her that her quotes are wrong, because forward direction you cannot get transition because I have the analytical results. So I was so convinced that I have analytical results which matched very well with the very large n. So whatever she is doing, that is wrong, and her quotes may be wrong. But now we know that as soon as we have some unstable orbit in between, you can get transition into the forward direction, which is not possible analytically. So in real world situation, it has huge application because all real world networks are finite in size. So any analytical calculation which we have done in thermodynamic limit may defy the predictions what we have made. So yes, it has applications in the real world situation, that we need to know that where the unstable orbit, if the system has the unstable orbits as well, in addition to the stable orbits. Okay, so there is can we find states which have significant higher order interaction but low synchronization? Low synchronization means, so before critical coupling, you have no synchronization. So when you say that higher order interaction, but still below critical coupling, you don't have any synchronization, but your question is low synchronization. So you're saying that you have synchronization. So with higher order. So actually, the thing is that, of course, you can get everything, all kind of behavior with this phase oscillator, okay? But can one give some generalized statement? Because, of course, if you put adaptation in K with the global adaptation, you can get some kind of tiered synchronization, etc. But I think you want to know that under what condition altogether one can get low synchronization. Is it because such kind of toy model, they are popular because any behavior you think about, you play something with this toy model, you include phase lag, you include adaptation, you even without network structure, even all to all with all the analytical things, you can get all the behaviors. But low synchronization, maybe I didn't get your question very well, or I don't have any generalized statement to make currently, perhaps. Okay, so Rohan is writing, with odd intention answers, it is easy to handle the questions. However, we lose the noise effect due to the finite size. Is it? Actually, mathematically modeling, like this paper, which this Pajo only, Diago, I am not pronouncing his name correctly. This paper he has done with the finite size, but for the pairwise interaction. So finite size, mathematically, analytically, he has made the semi-analytical prediction he has made for the finite size effect, which I am reading these days, and maybe we will have. So for higher order, as far as we understand, no one has done this finite, because higher order, you have very nice finite size effect. With pairwise, you have only supercritical transition, so you don't witness something very remarkable. So that's why people did not pay much attention. But finite size effect analytically, people have done for the supercritical bifurcation. So, but you are right, this noise effect, this Ott-Intenson is actually because we have continuity equation. So we have to go with the maybe Fokker-Planck equation to deal with the noise arising because of finite size in R. Okay. So coupling topology affect the synchronization. Yeah, this is very interesting question, Satish. So even the first paper by Alex Arenas in 2020 Nature Communication, they showed that some power grid model and cat brain area, and they showed in the real world system jump, but there was no data which we could found, etc. So real world networks, this jump, this is still an open question actually. So they have shown in their paper, but the data is not there. And later on, when we digged closely, we found that they made, because you know why we get jump. Okay, so mathematically we know that your R is equal to 0 solution becomes unstable, other solution become unstable, and you have one stable solution arise mathematically. But physically, if I would say, so you see the pairwise interaction that supports synchronization. So you come closer, so you have omega-1, omega-2, and you make stronger coupling strength. They try to come each other, and they fixed at some average value of frequency. Suppose there's 2 oscillator. So omega-1 plus omega-2 divided by 2, both attend this frequency. But as soon as you have 3 oscillator, so this is some kind of frustration. So you see, so higher order, so pairwise interaction try to bring them closer, but because of this K2 term, you have some frustration. So you are not able to make the giant cluster. But as soon as this pairwise interaction, which is supporting the synchronization, K1, as we are increasing the K1, there is one point, it overcomes that frustration and there is sudden jump. So this is the physical explanation of why higher order interaction is inducing such kind of phase transition. Now, if you take the real world system, so now you can see that in all-to-all networks, how many pairwise interaction you have? You have n square, nc2 pairwise interactions you have. And higher order interaction is nc3, which is one order greater than, so it's n cube kind of higher order interaction which we have. So that much interaction is there. Of course, it's a normalized. So you have sufficient higher order interaction to cause the frustration. But in real world system, your triangles, if they should be, whether they should be. So this is all open question, whether triangles should be homogeneously distributed in order to cause frustration, or their strength should be higher. So all open question, even numerically also. So can this analytical model apply in isotope acceleration? I'm sorry, I don't have any idea. Isotope acceleration. Maybe you can later on tell me in more details, and I whatever knowledge I have with this couple oscillator, I may try to help. But right now, I don't know anything about this. So Logesh, is it possible for a system of couple oscillators to exhibit multiple dynamical states? System of couple oscillators to exhibit multiple dynamical states for a single control parameter. So here single control parameter is K. So entire phase diagram, if K2 you fix, frequency distribution you take, and then it's only K1 you can draw the entire phase diagram. So here K1 is your that parameter which detects everything, entire, I skipped those slides. I can share also the slides with Sujit, and then he can distribute to you all. So this only K1 decides whether you get that Jacobian is becoming, mod of Jacobian is coming less than 0 or greater than 0. This K1 detects everything. So here K1 is that single control parameter. if that is useful to you.
I think we have finished the questions in the Q&A box, but maybe Professor Lakshmanan and Professor Ambika and some of the other people in the panel have questions you can ask.
Can I start?
Yes, please.
Yeah, very interesting talk, Sarika. So I like the point that the fluctuation induced by the finite size is it crosses the unstable branch, then sudden transition happens. So 2 points regarding that. In the reverse direction also, it's the same mechanism when you have hysteresis.
So the thing is that when you start with the synchronized state,
Yeah.
your fluctuations are not large enough. So their fluctuations are small, actually.
So what causes hysteresis then?
No. So just 1 second, maybe. So hysteresis is arising because of, not because of fluctuation. So hysteresis is, so this one maybe perhaps.
Yeah.
So here in the forward direction, when you have in the incoherent region, that fluctuation is large. So fluctuation can jump back. But in the reverse direction, actually, the fluctuation is not large. So in reverse direction, you never see. The fluctuations are very small. And hysteresis is because of you have saddle node bifurcation. You have one attractor here. So hysteresis is because of that you have two a stable branch separated by the unstable one, and which basin of attraction you are, your dynamics lies there, and that's because you have a hysteresis. So this is two different things, but you don't witness this because, and that also explained again in 2000 Strogat's paper, that when you have synchronized design, why you have less fluctuations, where in incoherent design you have more fluctuations. Yeah.
And one more question. Can we extend this to Landau-Stewart oscillators also, or is it only for phase oscillators?
No, Stewart-Landau, so this phase oscillator is coming from the Stewart-Landau oscillator. But anyway, so the question is, whenever we have unstable branch separating two stable branch, always we will see the finite size effect. This is the thing. So there also, if we have such kind of unstable branch separating two stable branch, then you should see this jump. Yes. Yeah.
Okay. Okay, good. Thank you.
Thank you.
Anyone else in the panel have a question?
Hello. I am Birayatunti, one of the PhD scholars in Professor Sujit lab. So in the same slide, with increasing the number of oscillators, I am seeing there is a delay in the onset to transition to synchronization. Is there any possible theory behind that? And is this observed in any practical systems?
Yeah. Like as we keep on increasing n, what is happening? This fluctuation is becoming smaller. So it will have more probability of transition when unstable orbit, this R value, unstable R unstable is having the smaller value. So because this fluctuation is smaller, so it has more probability to have that transition occurring when R unstable is taking the smaller value. But again, saying that if you run this simulation, like suppose we fix K1 is equal to 1, okay, and run simulation for very long time, there may have some value of T where it can jump here. But this is like more probabilistic. So you have more probability to have delayed jump as you keep on going to the large system. So this is the mechanism behind that we understand. But your second question was, what is the possible applications in the real world? So real words, yeah, it's the same. Like as you have large network size, you are more prone to follow the predictions made in the thermodynamic limit. So a small network size, one has to be careful to just simply apply the analytical predictions.
Okay, great. I think the question seems to be over from both the general audience and the panelists. So I want to thank Sarika for this wonderful talk. I really enjoyed it. And we are delighted to announce that our next webinar will feature Professor Klaus Lernes from the University of Bonn, Germany. This will be on February 24, 2025, next month at the same time. February 24th. Please mark your calendars and look forward to seeing you on February 24th. Thank you, Sarika, once again. And thanks everybody for attending.
Bye-bye.
Bye-bye, everybody.
Can I leave now,
Yes.
Sujit?
Yeah,
Thank
yes,
you.
that's it.